evening, everybody. Today it's the turn of Alma. So first of all, I just wanted to remind that you have to enter your name here in the table, usual table, so that at the end we can make the list of all the people that have the right to vote. Today it's the turn of Alma. Alma is one of our colleagues. She's enrolled in the PhD program of Structural, Seismic and Geotechnical Engineering. She has a double degree in Mechanical Engineering and Biomedical Engineering. So she has a sort of background which is different from us. And today she will explain how this background is important to have this kind of PhD research, which is about stents, you can see here. So she will talk about this research topic that she's developing with the professor Lorenzo Petrini. So, Alma, please.
Thank you, Angela, for the introduction, and hi, everybody. For those of you who don't know me, I am Alma. I'm a PhD student in Structural, Seismic and Geotechnical Engineering of the third year cycle. And I work in the area of theoretical modeling and mechanical characterization of biomaterials. As Angela said, I graduated in biomedical and mechanical engineering with a double degree here at Politecnico di Milano. And then I mainly specialized in the study of the fatigue behavior of cardiovascular devices made by nickel-titanium shaped memory alloys. So today I will present some of the results of my PhD research about a fracture mechanics approach for fatigue life prediction of nickel-titanium peripheral stents. In the cardiovascular field, the current trend of the medical industry towards less and less invasive procedures has increased the demand for flexible devices that can fit on small catheters and are characterized by spring-back properties. So in recent years, this has led to an extensive use of nickel titanium to design self-expandable devices for mini-invasive implantation to treat both pathologies affecting the heart itself or the vessels. Among these devices, we have, for example, the stents, which are adopted to treat stenosis in peripheral or carotid vessel due to atherosclerosis. We have prosthetic heart valves to substitute the native cardiac valves in case of regurgitation or stenosis, and also, for example, endovascular graft to treat aortic aneurysms. All these devices are obtained through a laser cutting process, starting from tubes with micrometric thickness, followed by a shape setting process and a sequence of thermal treatment to obtain the final shape of the device, which is a formula that is specific for each company. So through this process, it's possible to adjust the transformation temperatures of the alloy in order to obtain at body temperature, so at 37 degrees, a characteristic pseudoelastic behavior, which is related to a reversible thermoelastic transformation between an austenitic and a martensitic solid phase. When working above the so-called austenite finish temperature, AF, the transformation from austenite to martensite is induced by the application of a mechanical stress, with a resulting typical flag-shaped stress-strain response, with three different regions. There is an elastic loading of austenite in the first phase, then there is phase transformation at a constant stress level, and then elastic loading of the martensitic phase. Then, when the load is removed, the inverse transformation of the material allows to completely recover large inelastic strains up to 10% without any permanent deformation. However, this specific treatment sequence, which is applied by the manufacturing company to obtain the final device, determines a strong variability in the material behavior and in the resulting mechanical properties, with the need for an ad hoc characterization for each device. On the other hand, since it's not possible with current technology to obtain a material which is defect-free, the proprietary choice of the company has also an impact on the number of inclusions and the distribution of defect in the alloy, which are related to both the choice of the raw material in terms of purity level, but also on the applied manufacturing steps, which may induce surface scratches and flaws. This work in particular is focused on nickel-titanium peripheral stents, which are reticular devices which are constituted by a series of V-shaped struts connected each other by means of links to create a typical mesh structure. Nowadays, nickel-titanium stents are the gold standard in the treatment of atherosclerotic disease affecting lower limit vessels, where there is a reduction in the lumen of the vessel due to the growth of plaque of fatty deposits. So when the stent is implanted in the artery, it allows to expand the vessel and restore the physiological blood flow, so to reduce the risk of cardiac attack. During the implantation phase and the working life, the stent is subjected to a typical loading sequence, which is here reported. Starting from the stent, which is manufactured in its expanding configuration, so with a diameter of about 6 or 7 millimeters. The stent is crimped on a catheter for a mini-invasive implantation, reducing its diameter to about 2 millimeters, and is guided to the stenosis site. In this point, the stent is released from the catheter, and thanks to the pseudoelastic behavior of the material, it tends to recover its original expanding configuration, thus compressing the plaque against the wall and expanding the vessel. During its working life, the stent must then withstand millions of fatigue cycles, which are mainly related to gait, combining axial and radial compression, bending, and torsion. So the result is an high risk of fatigue failure phenomenon of the device, which typically starts in correspondence of pre-existing defects in the material, with potential dramatic drawbacks such as, for example, the restenosis of the vessels. Despite the great progress that has been done in the last decade in this field, nowadays the fatigue failure of nickel titanium cardiovascular devices is still an open issue of minor concern due both to the limited knowledge about the failure mechanism of shape memory alloys and the uncertain role which is played by phase transformation. For quality certification, the stents are required to survive up to 10 millions of fatigue cycles, corresponding to 10 years of working life in vivo. So typically, the manufacturing company adopted the so-called testing for survival approach to assess experimentally the performance of a device in loading conditions simulating in vivo boundary conditions. However, this approach is rather expensive, both in terms of cost and time, since it requires long and expensive experimental campaigns. It allows to verify just few task conditions, and it only provides a failed, not failed output. So recently, in silico studies have been recognized as a powerful complementary tool to provide a combined interpretative and predictive approach to evaluate the safety of a device in both a design and verification phase. So an hybrid phenomenological approach has been established, which relies on the combination of in vitro tests on the material and in silico studies on the device. So according to this method, first of all, it's necessary to characterize the static properties of the material through uniaxial tensile tests on ad hoc samples obtained from the same tubes of stents, and thus sharing similar dimension, microstructure, and thermal treatment. Then the fatigue behavior of the material should be characterized, typically in a uniaxial loading condition on similar ad hoc samples. Adopting, with respect to other methods, in this case, a strain-based approach due to the strong nonlinear response of the material characterized by stress plateaus. So typically the results are reported in a constant life diagram by defining the fatigue strain limit at a fixed number of cycles, typically 1 million, as alternate strain versus mean strain. So here you can see the fatigue limit curves of the material, and it's possible to see that for nickel titanium shape memory alloy there is an increase in the fatigue limit with the mean strain up to a certain threshold. Then to apply this method is also necessary to know precisely the geometry of the device, having a reliable CAD model, and to know the applied boundary conditions in vivo. Once having all this information, finite element simulations are performed on the device, applying a loading condition which resembles the condition applied in vivo, in order to compute the three-dimensional stress and strain test in each element of the model. Then this method required to introduce a fatigue criteria to convert the tensorial quantity into a one-dimensional equivalent index that can be compared to the fatigue limit of the material to evaluate the device performance. Here in the picture, each one of these blue squares represents the fatigue index computed for one element in the most critical region of the device, and it is compared with the limit curve of the material. However, as was demonstrated by our research group in previous studies in which several fatigue criteria developed for common metals were investigated, it's still not clear which is the most suitable criteria to be adopted for nickel titanium shape memory alloys, given their particular behavior, and also given the limited knowledge about its failure mechanism under fatigue loads. So beyond this standard approach, which focuses on the macro scale of the device and assume a defect-free material, recently damage-tolerant approaches based on fracture mechanics became popular as complementary predictive tools. So the starting point of this method is the intrinsic presence of defects in the material, which act as initiation site for the final fracture of the component, and thus this method accounts for the crack propagation process, focusing on the microscale of the material. So the aim of our study was to investigate the feasibility of this kind of approach in the fatigue assessment of nickel-titanium cardiovascular devices, providing a tool for both predicting the fatigue life of the devices, but at the same time for supporting the choice of a suitable raw material for a given application. So the standard damage-tolerant approach, which is applied for common structural metals, is based on linear elastic fracture mechanics, under the hypothesis of small scale yielding at the crack tip in normal working conditions. So according to this method, crack propagation tests are performed on ad hoc samples, applying a cyclic load with a certain load ratio between the minimum and the maximum load in a cycle. In this way, it's possible to obtain the evolution of the crack rate as a function of the stress intensity factor range, which acts as crack driving force and depends both on the applied stress and the crack size and shape. Then, by fitting the data in the stable growth region with the Paris law, it's possible to obtain the crack propagation parameters C and M of the material. And the crack propagation law can be integrated between an initial and final defect size to perform a fatigue life prediction of a specific component. However, as you can imagine, the application of this approach to nickel-titanium shape memory alloys is not straightforward due to the strong non-linearity in the material behavior, even in normal working conditions. So our purpose is to replace the stress intensity factor range with the cyclic J integral, which is an energetic parameter defined as a line integral on a closed path enclosing the crack tip, which accounts for both the elastic deformation energy, but also for the dissipation of inelastic energy during phase transformation at the crack tip. So the standard Paris law can be substituted by a modified Paris law, which involves the modified parameters C prime and L prime. And again, this can be integrated between an initial and a final defect to perform fatigue life prediction. More specifically, the formulation of the cyclic J integral that we adopted is the one proposed by our collaborator of the Department of the Mechanical Engineering, so the research group of Professor Patriarca, which defines the cyclic J integral as a function of both the defect size and shape, and given by the sum of two contributions, the first associated to the elastic deformation energy, and the second associated instead to the inelastic deformation energy, so in this case related to phase transformation. To obtain these energetic parameters, the stabilized stress-strain cycle is needed to compute the elastic modulus, the stress range, and the inelastic strain range. And then by fitting the upper branch of the curve with the Rambert's equation, it's possible to compute the hardening parameter M prime, which appears in the inelastic term. So to synthesize, the ingredient that we need to apply this kind of method is the stress-strain curve in the device during a cycle, the defect distribution in the material, and the crack propagation properties of the material. So to verify the feasibility of this kind of approach, we decided first of all to perform a proof of concept study on multi-wire samples, each one constituted by 9 parallel wires. These samples were obtained from the same source tube of stents and are characterized by a similar thickness and also a similar distribution of defect, but at the same time they allow an easier evaluation of the stress and strain state due to the backbone geometry. So a wide experimental fatigue campaign was performed by using an in-house setup with a closed hydraulic circuit to test the sample in water at 37 degrees. The tests were performed in displacement control, and the proper displacement sequence was applied to reproduce the crimping and the deployment phase of the device, followed then by the cyclic load at several combinations of mean strain and amplitude strain. So for each test, the stress strain curve was obtained by simply converting the force and displacement experimental data to obtain the needed stabilized cycle. And the experimental number of cycles to failure was recorded for each of the 9 wires of each sample. Then the fracture surfaces of the failed wire were inspected through a scanning electron microscope to identify the initial defect at the initial site of fracture. For each defect, the square root of the area was computed, and then by assuming a semi-circular shape of the defect, an equivalent crack depth was computed. Then a distribution of the initial defect size was calculated by fitting all the available data with a Gumbel distribution, also known as the largest extreme values distribution, to obtain the mean value of initial defect size equal approximately to 1.2 microns, and the corresponding 95th and 5th percentile values of the distribution. Then a proper shape factor was introduced by assuming the assumption of semicircular surface cracks, and by inspecting the morphologies of the fracture surfaces, final crack length at failure equal to the 75% of the thickness of the wire was assumed. So once defined the cyclic J integral, which acts as crack that reinforces the initial and final crack length, the last ingredient needed to integrate the propagation law is given by the crack propagation parameters of the material. So to collect this information, crack propagation tests were performed on notch samples having the same thickness of the wires, which were machined from a nickel titanium sheet. So the tests were performed by applying several load sequences with cyclic load at 2 different load ratios, 0.1 and 0.7. At the end of each loading step, 2 images were acquired. One reference image in correspondence of the minimum load of the cycle, and one image in the deformed configuration with the open crack in correspondence of the maximum load of a cycle. These images were then correlated through a digital image correlation to compute the crack length at each step. And so it was possible to obtain the evolution of the crack length as a function of the number of fatigue cycles from which the crack growth rate was obtained. Then for each one of the experimental crack length, a finite element simulation was performed in Abacus in order to compute the stress intensity factor range. So the result of all this procedure was the evolution of the crack growth rate as a function of the stress intensity factor range. Then, as previously explained, the stress intensity factor range was replaced by the cyclic J integral by exploiting the relation between these two parameters under the assumption of elastic loading in a plane stress condition, which is reasonable in the case of crack propagation tests since the small-scale yielding condition was always respected. So once having the evolution of the crack growth rate as a function of the cyclic J integral, by fitting the data with the modified Paris law, the crack propagation parameters C prime and N prime were obtained for the two load ratios. So moving back to our test on multi-wire samples, at this point we had all the necessary information to calibrate a crack propagation algorithm based on the integration of the crack propagation law between an initial and final defect, updating at each step the cyclic J integral, the crack size, and the number of cycles to obtain in output the number of cycles to failure in specific loading conditions. So here we have the results for 2 of the tested conditions, where the experimental number of cycles to failure obtained for the 9 wires of each samples on the x-axis is compared with the predicted number of cycles to failure on the y-axis. Here the vertical scatter band in the prediction is obtained by assuming an initial defect size equal to the mean value of the defect distribution and the 95th and 5th percentile values of the distribution. A perfect match between the predicted number of cycles and the experimental number of cycles is obtained in correspondence of the solid line, while conservative predictions are obtained below it. So, in all the tested cases, we were able to obtain promising fatigue-like predictions with a good matching between the experimental number of cycles and the predicted number of cycles and the experimental observation. Then, starting from these results, we started to investigate the application of this kind of approach to a stent resembling the conversion complete geometry, which was manufactured during our previous PhD thesis. So, to this purpose, the previous fatigue tests were exploited, in which 3 different devices were testing, applying a multi-axial load resembling vivo condition, combining axial compression, bending, and torsion. In the test, all the devices failed at about 20,000 of cycles, which fracture in correspondence of the peak of the V-shaped structure in all the cases. And also in this case, after the test, the fracture surfaces of the stent were inspected through a scanner electron microscope, highlighting the presence of initial defect with a size of approximately 1 micron and a crack propagation length of about 50 microns. In this case, the tests were supported by finite element simulations, given the complex loading condition of the stents, in order to be able to evaluate the local response of the material in the most critical region in terms of maximum principal stress and strain. So, in particular, 15 elements in the most loaded area were considered. Mode 1 propagation of the crack was assumed, so an opening of the crack along the thickness in the direction perpendicular to the maximum principal stress, which is here depicted. And for each one of these elements, the stress-strain cycle was computed. So, like exactly the same procedure that I described before. Also, in this case, we were able to obtain promising fatigue-like prediction for the stents, where here each one of the horizontal lines represents the prediction for one of the 15 elements. And the prediction is compared to the experimental range of number of cycles to failure, considering the 3 tested devices. Also, in this case, we have a perfect match in correspondence of the solid line, while we have a conservative prediction below the solid line. So, to conclude this talk, despite damage-tolerant approaches have not yet been widely used in the fatigue assessment of cardiovascular devices, this work represents a proof of concept study for the application of fracture mechanics method for both predicting the fatigue life of nickel-titanium devices, but also for supporting the choice of a suitable raw material for a given application by determining the size of the maximum acceptable defect. So, in particular, an approach based on the energetic consideration through the introduction of the cyclic J integral seems to be able to give promising fatigue-like prediction of both multi-wire samples and nickel-titanium stent. And this approach can then be further verified in the future on more designs and several loading conditions, exploiting our collaboration with the manufacturing company Alma. Then, what we aim to do with my PhD research is to investigate other methods for fatigue assessment and crack propagation modeling, combining both experimental and computational strategies to develop in the end an integrated predictive tool for the fatigue assessment of nickel-titanium cardiovascular devices. So that's all. Thank you for your attention.